Bismillahirrahmanirrahim. So we were discussing on the time shifting and the folding operation in the last class, during the last session. So if you have any question or any comments from the last session, anything to ask, you can raise your hand. Okay, otherwise we can start today's session. Okay. If we do, I have already mentioned that. So these operations like the time shifting, that means time delay or time advancing, and the folding operation, they are not commutative. So what does it mean? If we do the process in different sequence, that will not give you the same result. For example, if we start with the folding operation, and after doing the folding operation, if we do the time shifting operation, it will give one kind of result. Comparing with the operation, if we do the time shifting operation, and after that we'll go for the folding operation. For example, we can make this idea clear with a simple example. Let me segregate the portion. In the left side, what we'll do first, let's take that xn is our signal. I'd like to draw a very simple signal to make the point clear. So let's say this is 0, this is 1, this is 2, this is 3. At the location of 2, we have one stem. So that is our xn. This is our xn. 0, 1, 2, 3, and so on. Now, first of all, we have performed the time delay operation of xn. Sorry, folding operation of xn. If we go for the folding operation, yes, we know that after doing the folding operation, we'll find x minus n. And how it should be looks like, it will be folded back to the opposite direction. So it will be in the left side. This is -1, -2. At the location of -2, you will got the same stem, and otherwise that will remain the same. So this is 0, -1, -2, -3, -4. So this is our folding operation. After doing the folding operation, if we go for the shifting operation, time shifting with let's say 2 samples, the time delay for 2 samples, the k represent samples, number of samples of the x minus n. That means we have already done the folding operation. So it can be written as x minus n. We are shifting in the right. That means delayed by 2 sample. If k is equals to 2, let's say. In that case, how the signal looks like? The signal looks like this. We want to draw that. So we have this signal and now shifted 2 samples to the right. We know that -2 actually shifted to the right. Then you will find that this signal will shifted to the right with the 2 samples. So it will be implanted. It will be shifted to the center. And that is the result. So this is the result we have got. This is by the operation, first folding and then shifting operation. Okay. So you can remember this. It will be implanted in the at the center location. Now, if we do the things like that, if we first do the shifting operation for 2 samples from xn, so how it will looks like xn minus 2. So we can draw it here. We can draw this, and where the signals will be shifted. It was at the location of 2. Again, it will be shifted by 2. So it will be like 0, 1, 2, 3, let's say 4. At the location of 4, this sample will be shifted at the location of 4. So I have already drawn xn minus 2. Now, if you want to fold it, if you want to fold it, then where this sample will go? Definitely at the location of minus 4. So this is minus 1, minus 2, minus 3, and minus 4. So this will be shifted to the location of minus 4. And you will find that when you have made it like this, you will find that it will be shifted to the left with the location of minus 4. So you will find that this operation, that means the operation number 1, we have done the folding operation first, and then we have done the time delay. In the second one, first we have done the time delay, and secondly we have done a folding operation, and we have found they have given us the different results. So that's why these are not commutative in nature. So if your process or your system does something with the folding first and then time delay, you need to take care about that, the process, which one should come first and which one should go for the second one. Okay, we need to take care about the sequence, because sequence does matter for this case. Okay. Okay, from there we can also conclude that these operations for these two operations consecutively, these two operations are not linear in nature. That means you can't swap the operation before or after defining the process. Okay, we'll talk about the linearity of the system. As far I know that you also know about the linearity of the system. However, I'll just I'll give some example with some graphical representation. Okay, now there is another operation. It's called downsampling or the time scaling. First of all, we'll try to show the principle of the downsampling, and then we'll also talk about the usability of this kind of downsampling in DSP, digital signal processing. Okay, let's take that yn is equals to x twice n. Try to understand that xn is your mother sequence or original sequence. And this equation actually gives you the system definition. What does the system actually do? If I write like this, yn is equals to xn minus 1, what does the system do? The system made a delay. It is actually a delay circuit, something like that. If I write like this, yn is equals to twice xn. So what is that system? This is an amplifier which actually amplify your original signal with a multiplying factor of 2. If we write like this, yn is equals to x1n plus x2n, what does it mean? This system is an adder circuit which actually add two arbitrary input. So in that way, this equation actually we can represent it, or we can mention it as the system response, a system definition. So this is a system definition. Okay, we can mention it by the graphical representation in this way, or block diagram. This is tau. Tau means this is the system, and this is your output yn, and this is your input. And what is your output? The output will be represented by this x twice n for this case, for the downsampling. Okay, so we need to know how we can plot it and what is the purpose of doing the downsampling. let's take this example, simple example. We have these samples. So we have a number of samples. And now we try to, so this is our xn. Now we need to draw the yn. So take one by one. So let's take y0. So we are searching for what should be the value at this location. Y0 is equals to x2 into 0. So of course x0. So that means it will be the same value as at the center. So this is 0. What is the value of this sample? What is x0? That was 0 given in this diagram. Okay. Now we can move to what is y1. We are searching for that. That is x2 into 1. So that is x2. Where is x2? What is the value? So this is our x2. This is our x2. So that will be presented at the location of y1. So this is the same value as we have. So this value is equal to that value. Okay. So now you can understand that. What about this one? You are missing that value. You are not taking this value anymore. So you are missing some data. Similarly, if we try to find what should be the value at the location of 2, y2, that is equals to x2 into 2, that is x4. Where is x4? This is x4. That was 0. And that value will be replaced or been filled by the y2 or the location of 2. So you have 0. What about x3? You are not counting that value. So you are dropping some numbers. So that means in this case, you are dropping this value, you are dropping this value, you are dropping this value, and so on and so forth. So you are missing some data. You are missing some data, and ultimately you are getting this stem of the result. Still, if you can look into this, it actually looks like a sinusoidal signal. That means it actually represents the same signal, but with different time scale, because you are missing, or you are cut down some samples. So that is known as downsampling. This is known as downsampling. Why we should do that? Okay, for some particular purpose we may do that. For example, try to understand the fact. Let's say you are at the point of a transmission line. In a transmission line, let's say you have your signal xn, and it actually has a very high resolution. That means a lot of data within a very short period of time. Then you go for downsampling with a downsampler. That is a system, and you have downsampled it, and it might be like that x, not twice n, it can be 4n or any value. So that means you are missing how many datas? You are missing 3 datas in between. So if it is that if it is x4n, then the first value is x0. After that, you are taking x4, then you are taking x8, like that. What about x1, x2, x3? You are missing those 3 datas. Then x5, x6, and x7, you are missing those data, something like that. So after missing all those data, you are getting a downsample value. Okay, and then you are transmitting that value, and with the antenna or with the cable, you are receiving that data. And after receiving the data, you have something called upsampler that will upsample it. We'll talk about the upsampling later on. And you are putting the upsampler, and you can convert your original signal back. Okay, we'll talk about the upsampling. So this is how you can save the data transmission. If you already know that what should be the frequency or what should be the time frame of your original signal, you can downsample it and you can send it to your to the transmission end, and you can retrieve back your original signal. But of course, the Nyquist theorem should survive for all the cases. The Nyquist theorem should survive, and in this case, sometimes, of course, there is a possibility of losing some data. So that's why if there is a like a medical data, or if it is that is a music data, in that case you shouldn't do go for the upsampling or downsampling cases. But for some regular data like the voice data, you can predict it. So over a network or over a mobile network, you can always go for the downsampling from the sending side, and afterwards you can, in the receiving side, you can go for upsampling and convert it to the original signal. When you have a very monotonous data, let's say that I'm talking about xn, you have a very monotonous data, the changes are very small, then of course you can go for upsampling very in a very high ratio. For example, yn could be written as x l n, where L is the factor of the downsampling. So you can go for the downsampling with a very high rate if the data is very monotonous. That means almost equal value you are getting. So then you can cross some data and you can preserve some data to understand the overall scenario of the signal. Of course, it will give you some advantage. That means your transmission line can carry more data from other sources. If you can cut down some signal by downsampling, you can add some more signal from other channel as well. Okay, because as you know that all the channels have their capacity, full capacity, the highest rate of signal propagation. So if you can cut down some samples, of course you can add some other sources to transmit it through your transmission channel. One question could be asked, what about the frequency? If we do the downsampling, if you do perform the downsampling, what could be the frequency of the new signal? Let's say if I give an essence like this, if xn is equals to, let's say it has 2 kilohertz, what could be the frequency of yn, where yn is equals to x twice n? The example is given, already given here. What is the frequency of this signal yn? Any of you? This is important to understand, because whenever you are doing something in the time domain, what is that?
1 kilohertz.
Okay, it is 1 kilohertz. 1 kilohertz. One of your friends mentioned 1 kilohertz. Any other answer?
So 4 kilohertz.
Another answer is 4 kilohertz. Okay, so we have two results. Okay, let me discuss it. If we take it like this, this is a full period. Let's say the full period is, this is 2 kilohertz. Okay, take it like this. This is 1 second. So what is the frequency of this? Of course, 1 hertz. Now the full cycle is concised between 0.5 second. 0.5 seconds. So now what is the frequency of this one? Of course, this is 2 hertz. So the frequency is doubled with the original one. So of course, the 4 kilohertz is the right answer. As you can also see from this diagram, previously the signal was like this, and now the signal is like this. Of course, the frequency is doubled here. Okay, so by this way you can understand, if I have x twice n, of course it's actually double the signal. If we have x thrice n, it will be triple the frequency. If we have x 4n, it will makes it 4 times of the original frequency. Okay, now we need to think of, let me give you another example here. Can you draw yn is equals to x thrice n? Can you draw that? So which point actually, let's say, so in that case, the 0th sample will survive, the 3rd sample will survive, and then 6th sample will survive, and so on and so forth. And in that case, if I draw that, how it looks like, try to understand it. It looks like the 0th sample will survive at the 0th location. The 3rd sample will be survived at the 1st location. The 6th sample will be survived at the 2nd location, and that is a negative maximum. And then 6, then plus 3, 9th sample, let's say this is the 9th sample. 9th sample will be survived at the 3rd location. So you'll have the things like this. So you'll have something like this, and that is not anymore a replica of the original signal. So you have the alias of that one. You are not getting your original signal here. If you have yn is equals to x4n, in that case, you don't have any opportunity to get back your original signal. So that means whenever you are doing the downsampling, what you are doing, you are actually making stress your original signal. What does it mean? This is very important. We know this is our signal should be in between -pi to +pi, or in the f domain, this is in the omega scale, or in the f scale, it should be half to -half. So whenever you have your xt and you sampled it and you have found xn, let's say the maximum frequency was like this, you are here. Okay, you are there, where it is at the location of, let's say, pi/2. It's a very practical one. This is -pi/2. This is a profile of your xn. This is a profile of your xn. At this moment, what we are believing that in the xn, we have a lot of frequency component starting from 0 to some maximum value, and you sample it with a sampling frequency, common sampling frequency, and you got the maximum value at pi/2. Okay, pi/2. Now, what you have done, you are taking yn, that means you are doing the downsampling with a factor of 2n, that means with a factor of 2. If you downsample it, what will be the maximum frequency in the omega scale? What would be the maximum frequency in the omega scale for yn? If I want to draw the yn,
pi to -pi.
Pi to -pi. Very good answer. So that means it will be now stretched to the value of pi, because as we already mentioned that if this is 2 kilohertz, then it will be converted at 4 kilohertz. So then if it was like pi by 2 is a relative frequency value. Now if we go for downsampling, the frequency will be converted to the pi. So the frequency will increase. Okay, fine. At this moment, we are happy with that. That means we can again retrieve back your original signal because it is inside the pi, inside minus pi to plus pi. But if you stress it with the value yn is equals to x thrice n, then what will happen? That will stress the value is a pi by 2 multiplied with 3, isn't it? So this will actually increase the value. That will stress the value more than this. So that is 3 by 2 pi. And this is minus 3 by 2 pi, minus 3 pi by 2 or 3 by 2 pi. So 1.5 pi plus minus. And of course, due to this extension, we are introducing what? We are introducing the aliasing effect to your signal, and you can't retrieve your original signal back. That is why whenever you are doing the downsampling, you need to also think about the aliasing effect. You never cross the Nyquist frequency, Nyquist ratio, what it has been for the sampling of an original signal. Okay, so be careful on the downsampling whenever you are doing the downsampling of a signal. Okay. Now come to the point as upsampling. This is the equation for the upsampling. Yn is equals to x n by 2. So n by L can be any value. So let's say x n divided by 2. Then what will happen? If we consider the previous example, the same example, let me draw the downsample equivalent result. Again, the equation is like this: yn is equals to x n divided by 2. If we took 2 is the factor, then for the 0th sample, we are drawing yn. For the 0th sample, what would be the value? The same value, because yes, y0 is equals to x0. Now looking for the first sample, this is 0th sample, y1 is equals to x1 divided by 2, and that is half. What is the value at the location of x half? What is the value?
0.
Okay, basically it is actually undefined, so we are replacing it with a 0. Okay, so yes, your answer is correct that there is no data. That means we do not know what is there. So that's why we are thinking that, okay, that is a 0 value. Okay, so take it as a 0. I can so the 0th sample is 0. The first sample is also 0. What about the second one? Y2 is equals to x2 by 2. That is x1. What is the value of x1? This is the value of x1. So we can replace it with that. So this is a value at the location of 2. Similarly, what is xy3? You'll find that x3 divided by 2. So we don't have any value. So that means we can replace it by the value 0. What about y4? That is x4 by 2 is equals to x2. So that means the second sample is representing here at the yn at the fourth sample, like that. So now if I stress the result, you can find it very clearly that the output could be looks like this. 0, then again a 0, then small value, then 0, then large value, then 0, small value, then 0, then 0. And you having always, you have two values. So this value actually came from xn, this value from xn, 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 xn. Then you have always, you have extra 0 and then the actual value, extra 0, then actual value from your original signal, something like that. Now you can find that your signal is now space. That means previously your signal was like this. Now your signal looks like this. Still, you need to understand that we have something over there. What is the value there? This is 0, 0, 0. Those are the 0 values. So this 0 is actually came from xn, and this 0 is from the sampler that is by your system. What is your system definition? This is xn divided by 2. That is called upsampling. Why this is called upsampling? Because you are adding some more samples. You are adding some more samples in between two datas. That's why this is called upsampler. Why we should have this? Why we need that? Okay. If I start it from the beginning. So let me give you this example. Maybe it will take some time. Still, I believe that it will be very helpful for us. So I'm drawing xn. I try to draw it quickly. So this is our original signal, which we start with. Okay, so this is our original signal, and this is xn. Now from xn, what we are doing, we may do the downsampling first. We do the downsampling and we find yn. This is yn is equals to x twice n, and we have already know how it should looks like. It will take the 0th sample, it will miss one sample. So after that, it will take the higher value, it missed the second another data. Okay, then it will goes to the 0, and after that okay, so it will take this, take this, take this, and take that value like that. So it will take the higher value again. So from 0, after that it will get the higher value, then missing this data, then again 0, something like that. So this is our yn. This is yn. Yn, where yn is equals to x twice n. Now what we are trying to do, we are upsampled. This is downsampling, and now we are doing upsampling with the equation yn is equals to x n divided by 2. How it should be? It should be like that: 0, then extra 0, then we have higher value, then extra 0, then actual 0, then higher value negative, then extra 0, and then original 0. So let me write it like y prime n to make it understandable. Y prime n. Now, if we do something that if we make an average of this sample to this sample, if we make the average of that, how it looks, how it should looks like. Okay, So it looks like the average of that probably give you this data. If you make an average of this data to that data, it might give you this kind of data as well. If you make the average of this data to this data to this data, you will have almost zero or some negative value over there. Okay, probably I missed some value, whatever the case. Okay, so I have missed some data over this period probably. Okay, and if we have this, we'll got this kind of data. So I have missed one data over there, because this is 0, then extra 0, then actual value, then 0, original 0. Yes, there should be another 0 over there. Yeah, of course. So in that case, what we'll find, the average of that will give certainly 0, and the 0 and the higher value will give some higher value, and higher value and 0, that will give you some lower value over there, and then 0 over the next one will give you the 0. And ultimately you can retrieve back your original signal by making an average. There are some different algorithms, though there are some different algorithms. I'm just trying to make you understand the process very in a simplified manner, that okay, you can retrieve your original signal back just by making the upsampling. First of all, this is downsampling. Then what you are doing, upsampling, and after that you are making averaging, and then you can find your original signal back. So that what I have already mentioned, that you are sending your signal after making the downsampling. So that's why you can save a lot of data through the transmission channel. Whenever you got this data, then in your processor, by your processor, you can upsample that, because the processor is speed most of the cases is a higher or more capable, because you can give more power and other things, instruments in your receiving side, and you can upsample that, making it average, and you can get back your original signal. You can retrieve your original signal. Okay, so I believe that you got the idea. So again, if I ask you that, if you upsample the signal, upsample means this technique. If you do the upsampling, whether the frequency will increase or decrease, what will happen?
Decrease.
The frequency will decrease. So in that case, if we go to the frequency domain representation, minus pi to pi, if the original signal was like this, I'm talking about xm, if you upsample it with 2, then the frequency representation, the spectrum will be squeezes. That means the frequency will be downgraded, though this is called upsampling. The sampling is higher, but the frequency will be lower. So you do not need to care about the Nyquist theorem in this case, because it actually give you the it will not be stress to more than pi region. So it will be concentrated very close to 0 or a DC value. So it will be moved to the left. So that's why you do not need to care about the Nyquist ratio or Nyquist theorem. Okay, I believe that the total idea is very clear. Okay, the practical, for a practical region, this is very important when we are we'll talk about a multi-rate signal processing in your higher studies, like in your masters or somewhere else. You may heard about the multi-rate signal processing. There you need to change the sampling frequency within the period of your signal. Okay, you need to change it. Sometimes, yes, sometimes you have a sampling frequency and you need to change the sampling frequency in other places. There it comes the multi-rate signal processing. there these two terms, upsampling and downsamplings, are very much important to understand. Okay. Very quickly, we can say that, okay, there are some other scaling like amplitude scaling, the summation, the products. Okay, those are very simple tasks. So how they are representing, how they can be represented in by the equation, it has also been given here. Okay. Okay, discrete time system. We may define the discrete time system. So this is just a definition. A discrete time system is a device or algorithm that operates on a discrete time signal called the input or excitation according to some well-defined rule to produce other discrete time signal called the output or the response of the system. That means if you have a discrete time signal and you have a system, you have discrete time inputs that can be also mentioned as excitation or input according to some well-defined formula. What is a well-defined formula? Like upsampling or downsampling. There should be some well-defined formula by which you can generate the output, which is known as response, that is known as discrete time system. So very simple definition, but the key thing is your input should be discrete, output should be discrete, and the system should be well defined with some formula. That is called the discrete time system. Yes, the system is all can be represented like this. What is tau? Any kind of thing. It can be adder, subtractor, multiplier, integrator. It can be upsampler, downsampler, anything. Okay, so this is in general system representation. You can get more idea on this system representation by the example 2.2.1 from the Proteus book. So please go through that. The input-output relation of the accumulator can be written as, so we are giving some example of the discrete system. The accumulator, that means it is also an adder. You can say an adder with multiple inputs. The input-output relation of the accumulator can be written as by this equation. What is this equation? This equation is the system representation, the system definition. So you can define your system with this equation. Okay, so this equation shows that, what does it mean? You have a number of inputs and you are summing up. For example, you have x0, then x1, then x2, something like that, and you are summing all those things up to infinity. If you want to sum up all those things, how many memories you need? You need, for this kind of summation, you need infinite number of memories. On the other hand, what we can do, we can take the present data and we can store the previous sum data. For example, let's say you need to add 2, 3, 1, 5. You need to add those 4 numbers. We can do it in two ways, like 2 plus 3 plus 1 plus 5 all together. You can add this, or what you can do, you can add 2 plus 3, that is 5. You can store it. Then 5 plus 1, that is 6. You can store that, and then 6 plus 5, that means 11. You can have your result. In the second case, in this second case, you need actually a, let's say single memory to store the output, and the output is added with the present input. Output is added with the present input, And that is how we are presenting here as well. So this is the output, the previous output, and added with the present input. That is how we can represent our accumulator. On the other hand, we can represent it like this. All the inputs all together you are adding. So that means all the inputs you are adding. So what is the difference between these two systems? In the system number 1, you need more memory location for storing those data. In the second case, you need actually, conventionally, you need actually 2 memory location. One is the input, previous output, and the recent input. Previous output and recent input. Previous output and recent input. All the cases you need just a single memory location, 2 memory location to get the output. Even for the infinite number of summation, you need only these 2 memory locations. Or exactly, if you want to say that you need 3 memory location, 1 is for the output and 2 is for the input side. But in the first case, you need exactly infinite number of memory locations. So of course, the second one is more convenient for the mathematical, physical purposes. So this is the way you can represent your discrete system for the accumulator. The previous output and the inputs. Previous output and present input. This is the block diagram representation of the discrete system. We need this block diagram representation. Why we should know this block diagram representation? Because whenever the system will be more complex, first of all, you need to present it by the block diagram to understand the system. And then you can normalize or simplify your system as well. And so there will be some tradition. So in this section, we are just talking about this tradition. You can go through this and you will find it very simple. Still, I'm just showing it. So this is an adder, of course. So this symbol shows you the adding of 2 signals. This is a constant multiplier. How we are presenting constant multiplier. This is the way we are presenting the constant multiplier, where yn is equals to a xn. This is signal multiplier. Signal multiplier means this is a variable. So x1n is your input and y1n, x2n is another input or another variable. So then we can represent it like this. So this is a symbol of multiplier. This is for the variable multiplication. Unit delay, if we want to represent this kind of thing, this is by the equation and this is by the flow diagram or block diagram. So unit delay is represented by z to the power minus 1. Unit advance, it is represented by only z. So if you need 2 delay, z to the power minus 1 and then z to the power minus 1 again. If you need 2 advance, z and then again z, like this. Okay. Multiple delayed or multiple advance element. Upsampler can be represented like this, up with this, and downsampler with representing by this symbol. In your circuit or in your system, if you need this, you can write it with these sequences. So examples are given in this section 2.2.3. So you please go through that with the book of Procteus. It will be helpful, inshallah. Classification of discrete time system. We are actually talking about this classification from the previous classes. Static and dynamic system. What does it mean by the static and the dynamic? So let me recite this and then we'll give some example. A discrete time system is called static or memoryless if its output at any instant n depends at most on the input sample at the same time, but not on past or future samples of the input. That means if your system output is depends on xn plus, let's say, 3xn, that means it actually 4xn. It actually depends on only your present value, no past value or future value. So this is a static system. Another example, yn is equals to, let's say, x cube n. This is also x cube n plus twice xn. This is a static system because it only depends on the present input x0. Whatever the value you are putting, n equals to 0, you are having the present input value. On the other hand, if your the output depends on x n present value as well as x n minus 1, or yn is equals to x n plus x n plus 1, this is the future value, present value as well as future value, present value as well as the past values, then those are known as dynamic. So if and only if it depends on the present values, then it's known as static. If it is not a static one, it must be a dynamic system. So that is known as a dynamic system. And examples are given here. Okay, you'll find it very simple. These are the example for the static system, and these are the example for the dynamic system. Time invariant versus time variant system. Okay. Today we may start that, and if we have any confusion, we can clear it up in the next session as well. The system is called a time invariant if its input output characteristics do not change with time. I believe that you already know about this. Just give you some example to make the idea more concrete. A relaxed system tau, so this is the system, is time invariant or shift invariant if and only if, what is the condition? The input given to the system and you have the output implies that you are shifting your input and give it to the same system, and it will be like your output with a shifted version. More clearly, if we can say that, please follow this example. We have input given to the system. We got the output. And now this output is delayed by k sample. And that can be represented by yn minus k. Then if I ask you, what is yn minus k? That is nothing but you have your output first and then shifted by k sample, then you have n minus k. Okay, very simple. On the other hand, if I give the input to a delay circuit, first of all, and we got the delay, the input is delayed, and give it to the system. Which system? The same system we have discussed previously. Give it to the system. Then we got the output. So if I ask you what is yn comma k, your answer should be that we have input and then shifted it with n minus k samples and give it to the system. What is your output can be represented as yn comma k. So that is the difference between yn comma k and yn minus k. If they are equal, then this is known as time invariant system. Not the signal. Time invariant system. Where is that system? This is that system. We are talking about this system. Because it actually not depends on the time delay of the input or the output. Sometimes we can delay our input and give it to the system is equal to we are give it to the system first and delayed the output. Both are the same. In that case, this is known as time invariant system. Otherwise, if they are not equal, then this is called time variant system. Okay, so the examples can be given. Just we can start it today. Maybe it takes some time to discuss it with the graphical representation. Okay, so if they are equal, then this is time invariant. If they are not equal, then this is time variant system. These are the example. Example number 2.2.4. This is from the book. Okay, try to look it very closely. Xn is equals to yn minus nx n minus 1. What is this? This is the system definition. This equation is referred to as system definition. Now, since we have yn already, what we can find yn minus k directly. We are putting yn minus k, replacing all the n's with n minus k. All the n with n minus k. Actually, what we are doing, we are shifting it. We are shifting. Try to understand graphically. If we want to shift our y value with the k samples, the x n should be shifted by k samples. So we can write x n minus k. Similarly, x n minus 1. How many samples it should be shifted as well? It should be shifted by k samples. So that's why I am writing in this way, n minus 1 minus k, because you need to shift it by k sample, practical. And then you need to subtract first term to the second term. Okay, fine. What about yn comma k? Yn comma k means that first your input should be shifted. Input should be shifted. You have xn, it should be shifted by k samples, so n minus k. Now give it to the system. If you give it to the system, you'll find that that will subtract two terms. So if you are give it to the system, what it will do, it will make xn converted to that one xn minus k, because it is already been shifted. So that will come here, and minus will be there because that is the system definition. And what is your xn previously? That was xn. Now it is xn minus k. So we need to replace it by xn minus k. That is your input, and minus 1. This is from the system response. So this is minus 1. And from these two equation number 1 and 2, we found that they are equal. And that's why this is time invariant system. Okay, we'll show it in the next class with the graphical representation, number 1, and with some other examples, practical examples. You can go through this number B. It is from the book. So please go through this and try to understand that. I will talk about this in the next section, next class, inshallah. We'll also try to understand that whether this is downsampler. Downsampler is a time variant system or time invariant system. We try to understand it with the graphical representation in the next class, inshallah. Okay, thank you very much for your participation.